Okay, hello everyone. Always good to have you here. We're about to begin our presentation today. I think everything is ready on our side. So, all right. Today we're going to talk about something a little bit different from what we usually do. Once again, in this course, we usually talk about transformer maintenance and transformer oil and energy sector, but we also, Globcore also does some other things, and we have certain equipment and technologies for bitumen or asphalt processing, modification and such. So we thought that we might do a presentation on this topic, and it might be interesting to quite a few people, we thought, and so here we are. So what we're going to talk about today is production of modified bitumen, how this is done, and what are our suggestions on how to produce modified bitumen. Now, during the course of the presentation, I'm sure there will be questions. I have my colleagues here who are going to answer these questions in the text chat. And we're not going to stop the presentation to answer questions, just to preserve the flow, I guess, and the continuity. So if for some reason there is not enough time to answer all the questions, then we have all these questions recorded. If so somebody asks a question and does not receive the answer within the time frame of this presentation, that somebody will get back to them with answers. So with that out of the way, I suppose we can begin. And yes, here we go, the next slide. So bitumen. First off, let's recap some history very quickly. So the history of bitumen usage by mankind goes back to about 5,000 years. In between the rivers of Tigris and Euphrates, the cradle of civilization in Asia, in Persia and in India, bitumen was used as a protective and binding material. It was also used in Rome by ancient Romans for construction work and for protection of water. However, during the construction of roads, bitumen did not find any real application for a very long time. Even the Romans, who are pretty famous for their road structure in Europe, still did not use bitumen to construct the roads. Next slide. Further development of the application of bitumen technologies only began much later in the Common Era. In 1712, Dirigny discovered a bitumen deposit in Switzerland, and he experimented with mixing small pieces of natural bitumen with rocks, and a few years later he presented a thesis that was called Natural Asphalt Binder. And the bitumen that was used during that time and over the next 150 years was natural bitumen that mostly came from the island of Trinidad. However, later humanity discovered or invented the oil distillation process, and so ended the era of using naturally occurring bitumen. At first, mixtures of natural bitumen with oil distillation products were used, and later on, preference was given to distilled bitumen. This was facilitated by the research of one Desmet, who in 1881 patented the technology of blowing air over hot bitumen to obtain the so-called oxidized bitumen. Next slide, please. So for some time, advances in science and technology were sufficient to meet the requirements of the road construction industry, but the traffic intensity obviously constantly increased, as did the load on the road surfaces, and these loads obviously cause destruction and deterioration of the roads. And despite the fact that technology of oil distillation was improving all the time, the quality of bitumen as a distillation product actually only got worse, and the deepening of oil refining in order to increase the output of fuel, oil components, lighter fractions, it led to a deterioration in the quality of bitumen. In practice, unmodified bitumen demonstrated the following disadvantages, basically. It has high thermal sensitivity, means that it softens at high temperatures, and it's brittle at low temperatures. It has low elasticity and poor physical properties, and it tends to age fairly quickly. slide, please. So what the only way actually to get bitumen with the required properties was to use additives to mix into that bitumen. One of the first additives that was used was rubber. First natural rubber, and then all types of synthetic rubbers. For the first time, the introduction of rubber into bitumen is mentioned in British patents, and the first patent for such a mixture belongs to Hancock. In America, a similar patent belonged to Charles Nelson Goodyear, and in 1844, Castle patent appeared for the use of such compositions in road surfaces. So the first experimental sections of asphalt concrete pavements using modified bitumen were built in a number of Western European nations in the 1930s. And many areas of asphalt concrete pavements using modified bitumen have actually proven themselves very well under heavy traffic loads. And the advantages of modified bitumen began to emerge and become quite apparent. Next slide, please. And here we go with the advantages of modified bitumen. First off, it has pretty good contact with mineral materials. It has good low temperature flexibility and elasticity, and it doesn't tend to melt and flow as much at high temperatures at the same time. It quickly relieves the tensions and stresses that appear in the road surface layers due to traffic loads. It's quite resistant to fatigue loads that occur with cyclic temperature changes. It's rather frost resistant, and it actually has an extended temperature range for operation without destruction. It has increased hardness and physical strength as well. So the issue of getting bitumen with the required properties is relevant even now, because grades of road bitumen do not meet the requirements of road construction in terms of low temperature crack resistance, heat resistance, elasticity, adhesion to materials, especially with respect to the surface of mineral materials from acidic rocks, and aging resistance too. So even modern technologies for the production of bitumen do not give much possibilities on this regard, because the improvement of one parameter of the quality of bitumen will inevitably worsen some other parameters. So for example, an increase in the softening point is often accompanied by a deterioration in fracture resistance, or an expansion in the plasticity range reduces the resistance to aging, for example. Next slide, please. So, as I mentioned before, the main purpose of introducing modifying additives into bitumen is to reduce the temperature sensitivity of the binder. That means to increase its hardness in summer and decrease it in winter, and also to get it to be more elastic. So the ability for reversible deformations over the entire range of operating temperatures. So if this goal is achieved, then asphalt with the use of modifying additives actually has increased shear resistance, low temperature crack resistance, and fatigue durability. So today polymers is what we most often use as modifying additives for a road bitumen. And practically every known polymer out there has been tested in bitumen polymer compositions. However, the range of the polymers that we actually use is somewhat limited. A necessary condition for producing polymer bitumen binder is the compatibility of both ingredients, meaning the ability of a polymer to dissolve or swell in a bitumen dispersion medium. Among polymers, we have elastomers, thermoplastics, and thermoplastic elastomers, and these are the most commonly used ingredients in road construction. Elastomers are basically polymers with high elastic properties over the range of operation conditions. This would be synthetic rubbers of various physical forms. They can come in the form of powder, grains, or actually even liquid. Ethylene, propylene, butadiene, etc. So rubbers modify both bitumen and asphalt concrete mixture. There are thermoplastics, meaning polyethylene, atactic polypropylene, also known as APP, ethylene copolymers, ethylene vinyl acetate, EVA, copolymer of ethylene and acrylic acid, also known as alloy. Thermoplastic elastomers are polymeric materials capable of reversibly passing when heated into a highly elastic or viscous flow state. And these are styrene block copolymers. So styrene, butadiene, styrene, also known as SBS. and SEBS with addition of ethylene, and also SIS. That stands for styrene isoprene styrene. So modification of bitumen with elastomers causes an increase in the softening temperature, a decrease in cold flow, a decrease in the dependence of penetration on temperature, a decrease in the brittleness temperature or brittleness point, the ability to withstand multiple elastic deformation, and an increase in extensibility. Rubber is introduced into bituminous materials in the form of clumps, usually granules. It can be introduced as a solution in liquid hydrocarbons, can be powders, latexes, and it can also be dispersions in non-aqueous medium. The introduction of thermoplastics increases strength, cohesion, fatigue resistance, it prevents cracking, and at the same time imparts elasticity and reduces susceptibility to temperature fluctuations. Thermoplastic elastomers are a class of synthetic polymers consisting of hard and elastic segments, the combination of which provide thermoplastic elastomers with both high strength and elasticity. Flexible and resistant bitumen coatings are obtained by adding styrene butadiene rubber to bitumen. The most widely used polymers of the SBS type are these SBS polymers are used mostly because of their ability not only to increase the strength of bitumen, which is achieved by other types of modifiers, but also to give the polymer bitumen composition elasticity, which is a property inherent to polymers at rather low concentrations. And we're talking a range of 3 to 5% by weight of bitumen. The use of bitumen modified with an SBS polymer in the asphalt mix provides the road surface with the ability to quickly relieve the stresses that arise across the surface due to traffic loads. Next slide, please. Right, so according to modern understanding, bitumen is a complex colloidal dispersed system in which the discontinuous phase, asphaltenes, is surrounded by a layer of polar resins that form micelles. And these micelles are immersed in a continuous maltenic phase, which is a mixture of aromatic and saturated hydrocarbons. Therefore, it is believed that polymer-modified bitumens are a sort of a colloid and a colloid mixture. Next slide, please. In bitumen polymer mixtures, both dispersed phases, that is asphalt resinous substances and added high molecular polymers, compete with each other for a dispersion medium. Styrene and butadiene are compatible with aromatic and non-aromatic components of bitumen respectively. And it is this property that explains the strong interaction between SBS and bitumen. Butadiene blocks mixing with bitumen swell and absorb a significant part of the maltenic fraction, while polystyrene blocks, less compatible with bitumen, fall apart into isolated domains, thereby providing positions for lateral links. Depending on the ratio and chemical structure of the components of the dispersed phase and the dispersion medium, a special structure of asphaltenes in a swollen polymer network is formed above a certain critical concentration of the polymer, what you could call the critical concentration of structure formation. And this structure can be a spatial network of polymer within the coagulation framework of asphaltenes, or a spatial network of asphaltenes and polymer. And these polymer structures impart their mechanical and rheological properties to the original bitumen. At low polymer concentrations, the compositions can be considered as dispersion strengthened. In this case, hardening occurs because the dispersed particles impede the movement of dislocations in the matrix, that is the bitumen. The degree of hardening is proportional to the resistance of the particles to the movement of those dislocations. And this effect is observed when the content of the dispersed phase polymer is, say, 2 to 4%. If you look at the properties of polymer bitumen compositions with a 3 to 5 polymer content, you will find a noticeable decrease in the brittleness temperature without increasing the deformability. It's obvious that a decrease in the brittleness temperature actually occurs due to an increase in strength. At a higher concentration of polymer in bitumen, the compositions can be considered fibrous or layered. The matrix turns into a medium that transfers the loads to the fibers, and in the event of fiber destruction, breaking, it redistributes, the stresses. Such compositions are characterized by increased strength, elasticity, and resistance to fatigue fracture, which is especially necessary to ensure the operational reliability of the material. The process of destruction of such composite materials begins with the growth of microcracks, and then upon encountering a particle of high modulus rubber or polymer, it slows down, then decreases and even stops altogether due to relaxation of overtension at the tip of the crack. Next slide, please. All right, so the good performance properties of modified bitumen facilitate the use of such modified bitumen in quite a few fields. Among the most typical applications are road construction, asphalt concrete of the top pavement layer, surface treatments, protective layers of cement concrete pavements, crack breaking membrane type layers. It's used for preparation of drainage asphalt and bitumen elastomeric sealing mastics. It's used in hydraulic engineering as well for coating of potable water storage tanks and lining of water supply pipes as well. Coatings by modified bitumen provide very reliable protection against leaks in pools, reservoirs, dams, etc. It's also often used in roofing, I'm sure. Everybody's aware of that. Modified bitumen is used in the production of roofing felt, roofing shingles, and waterproofing cardboard. That is the waterproofing materials for all sorts of roofs in industrial, civil, and any other kind of structure. Next slide, please. So the composition of polymer modified bitumen includes viscous road bitumen, a polymer, and a plasticizer. Therefore, a change in the quality and quantity of one of the components inevitably brings about a change in the quality of PMB. And PMB is a polymer modified bitumen. Studies have found that the properties of PMB depend on the properties of its ingredients, while the type of dispersed structure of bitumen has the most significant effect on the properties of the material. And we distinguish bitumen of types 1, 2, and 3, which can be identified with colloidal systems of gel, sol, and sol/gel. For simplicity, we can represent the structure of bitumen as consisting of an asphaltene core surrounded by a shell of absorption solvation layers of resins. And these aggregate particles are distributed in the oil environment. Type 1 bitumens have low resistance to oxidizing factors during processing and the production of asphalt concrete. The advantages of type 2 bitumen are high cohesion and deformation resistance in an elastic viscous state, increased resistance against oxidative factors that cause aging. The disadvantages are lack of elastic and elastic plastic states, low heat resistance, and poor water resistance. Residual bitumen mainly belongs to this type. The structure of type 3 bitumen is considered optimal for road construction. This type of bitumen does not have any obvious disadvantages that are common to type 1 and 2. Grades of road bitumen that correspond to the type 3 are recommended for use in all roads and all climatic zones. The introduction of a reactive surfactant into bitumen of structural type 2 can lead to the transformation of that structure into type 3, so that can be changed. Next slide, please. So for the formation of a special structure mesh in PMB based on road grade bitumen, the minimum polymer content is 2 to 2.5%, and on the basis of petroleum bitumen, it's 3.5 to 4%. An increase in the content of SBS type polymers above the specified minimum is necessary if it's required to increase the softening temperature, extensibility and elasticity at temperatures of 0 centigrade, as well as when we work with low viscosity bitumen, petrochemical bitumen, and type 1 bitumens. An increase in the content of oil plasticizer is necessary in the following cases: to reduce the brittleness temperature, to increase elasticity and extensibility at 0 degrees centigrade, and uniformity of PMB, or when working with high viscosity bitumen, for example, 40-60 road bitumen. And also with petroleum bitumen and type 1 bitumen to increase its, workability and compaction of polymer asphalt concrete mixtures. Next slide, please. So there are several systems for assessing the quality and parameters of bitumen that are used in the world. There is the European system. It's reflected in the standard EN 12591 2009, bitumen and bituminous binders, specifications for paving grade bitumens, and there is the American SHRP SuperPave system. At the heart of the European system, bitumens are classified according to the penetration index. That is, according to the depth of penetration of a needle into the bitumen at a temperature of 25 Celsius, with only a small difference in the ranges of zone separation. The main indicators included in the European quality certificate for bitumen are needle penetration depth, the soft point, and resistance to aging, assessed by residual penetration. There's change in softening temperature and mass loss after heating at 163 centigrade. The regional norms of the European standard, in addition to the mandatory ones provided by the standard itself, include such requirements as the penetration index, dynamic viscosity at 60 centigrade, frost brittle point, and a kinematic viscosity at 135 degrees centigrade. And that is measured using a capillary viscometer. Next slide, please. In the case of low viscosity bitumen, the requirements are simplified and reduced in volume. The leading indicator of the consistency of low viscosity bitumen is penetration, the same as viscous bitumen. Within its limits from 250 by 0.1 millimeter to 900 by 0.1 millimeter, there are 4 grades of bitumen that are classified here. 250 by 330, 330 by 430, 500 by 650, and 650 by 900. Next slide, please. On this slide, you can you can see the primary or basic common tests that are performed for road bitumen. It's penetration, softening point, and frost brittle point. In terms of physical and chemical parameters, bitumen must comply with the requirements and norms that are specified in the standards. Next slide, please. Now, the American SuperPave system of standards was developed from 1987 to 1995 as the traditional indicators for assessing the quality of bitumen that were used for many decades in the standards came under serious criticism. The main argument against those old standards boiled down to the fact that those indicators didn't meet the operating conditions of bitumen in actual roads and were only based on practical experience and empirical dependencies and not on any fundamental physical or chemical principles or laws. And the SuperPave specification system focuses on the determination of the rheological properties of those binders, taking into account 3 life cycles or stages of bitumen. The first stage being transportation and storage of bitumen. Second being changing of properties of bitumen during the production and laying of the asphalt concrete mixture. And the third stage being the change in the properties of the binder during its lifetime when it's actually applied on the road surface. The accepted classification of bitumen, according to the operational conditions of the road surface, takes into account all stages of the use of bitumen, from an oil refinery to the use in the production of asphalt mix, and its use in the pavement after a certain period of time. In accordance with this system, the entire territory of the United States is divided into 37 road and climatic zones, which are called performance grades or PG. The division is based on the operating conditions of bitumen at low temperatures, meaning the temperature of the coldest winter day, and the highest summer temperatures, which are defined as an average temperature for the 7 hottest days. And based on these air temperatures, the temps of the upper layer of the asphalt concrete pavement corresponding to them at a depth of 2 centimeters is calculated. So the designation of the binder grade, for example, PG 8234, means that it should work well at a high coating temperature, up to 82 degrees, and at low temperature down to minus 34 degrees. And if it's PG 4634 zone, then respectively, we're looking at temperatures of 46 and minus 34. And between these extremities, according to the operating conditions of bitumen in the layer, there are another 35 zones in between. So the principle of selection and use of binders is that the values for all quality indicators included in the standard at certain temperatures should be the same. That means in any zone, all and every binding material must provide the same performance properties of asphalt concrete. At temperatures from plus 46 to plus 82 degrees, they must be sufficiently strong. And at temperatures from minus 10 to minus 46 degrees, they must have the same resistance to cracking. So the gradation of zones for low and high temperatures is made at 6-degree intervals, so like steps. As an example, this slide shows the requirements for bitumen grades PG 4634, 4640, and 4646. As indicators for assessing the suitability of a binder for each of the zones, the following are used: true viscosity, shear index before and after aging in a thin layer or under pressure, modulus of stiffness, critical deformation, and coefficient of plasticity. Next slide, please. So true viscosity is a technological parameter that allows you to evaluate the ability to pump a material through pipelines and its ability to combine with stone material. It's determined at 135 degrees centigrade using a Brookfield rotational viscometer. The principle is to measure the resistance of the bitumen layer located in the gap between the rotor and stator to shear at a certain rotor speed. The viscosity is automatically determined from the known torque and known rotational speed. It is accepted that the viscosity of the binder at a temperature of 135 degrees centigrade for all binders should be no more than 3 pascals second. To assess the strength of bitumen at high temperatures corresponding to a particular zone, the complex shear modulus G and the tangent of the angle of mechanical losses are determined using a dynamic shear rheometer, which performs sinusoidal oscillations in a plane-to-plane pattern with a frequency of 10 radian per second. To assess the correct resistance of bituminous binders, several indicators are used. The first is the stiffness modulus at a temperature 10 degrees centigrade below the minimum asphalt concrete temperature adopted for each zone. And the stiffness modulus must be equal to or less than 300 MPa. It's determined using a special device, a beam rheometer, which makes it possible to estimate the deflection of a bitumen beam pivotally supported on two struts with a load placed in the middle of the span. And this device is called the bending beam rheometer. On the road surface at low temperature, bituminous binders are subjected to stretching. In this regard, one of the criteria for assessing crack resistance is their deformability at low temperatures. As a result of the test, the temperature is determined at which the specimen tested in tension at a speed of 1 millimeter per minute breaks, when deformation, relative elongation actually, is not less than 1%. So for such tests, it's extremely important to ensure high measurement accuracy. So for that, laser micrometers are usually used, and the temperature is maintained with the precision of plus or minus 0.1 degree centigrade. So in the American system for assessing the quality of bitumen binders, great attention is paid to the change in their properties over time at the stage of processing, manufacturing, and during actual use on the roads. And this change can be defined by the term aging. So the SuperPave system provides two types of aging tests. The first aging test is performed by the RTFOT method in a thermostat with a drum rotating at a speed of 15 RPM, in which 8 cups with a thin layer of bitumen are installed. Each sample is blown with a stream of air, and the test temperature is 163 degrees Celsius, and the process takes 85 minutes. Samples after such heat aging that simulate technological processes are tested in order to determine the loss of mass and modulus of rigidity. This method is used to simulate aging during the preparation and laying of asphalt concrete mix. The remaining binder then is scrapped off for a pressure aging test. Now, the pressure aging test, the PAV, done in a pressure aging vessel, is designed to determine the influence of the environment during the operation of asphalt concrete on its crack resistance at low temperatures in terms of the stiffness modulus, plasticity coefficient, and or its ultimate deformation. So a pressure of about just over 2 MPa is maintained in the aging chamber with the help of compressed air. The thermostat and temperature is set in the range from 90 to 110 degrees centigrade with an accuracy of plus or minus half a degree. Cuvettes that contain 50 grams of binder are kept in the chamber for 20 hours. The cuvettes removed from the chamber are additionally kept at a temperature of 163 degrees centigrade for 30 minutes in order to remove the air that is absorbed by bitumen. And bitumen after this process is tested for is tested in dynamic shear rheometers, in bending beam rheometers, and in dynamic tension tests as well. So the advantages of the SuperPave methods include the following. Application of fundamental physical and mechanical characteristics of the binder, a uniformity of requirements for various types of binder, the relationship between the requirements and the actual operating conditions of the road layers, It gives an accounting for the aging of the binder and accounting for the process of its preparation and operation as part of the asphalt concrete pavement, and the use of computer technology in research and processing of results, which provides for quite precise measurements. The main disadvantages of this system, however, are as follows. It requires expensive and complex equipment, and the cost can run up to $350,000 to $500,000 approximately. It needs highly qualified personnel in testing laboratories, and laboratories, as I mentioned, must be well equipped. The tests take quite a bit of time, so duration of tests might be a problem. It does not take into account the effect of mineral substrates on the properties of bitumen, and it excludes the possibility of assessing the adhesive and cohesive properties of binders. It should be noted, however, that the existence of the SHRP superpave system does not mean a complete rejection of the previous bitumen quality indicators. In laboratory practice in the United States, the depth of needle penetration to identify the AC20 grade of bitumen, flash point, solubility in organic solvents, true density, and softening point are also used. These indicators in the USA are part of the so-called SHRP Plus package of requirements. So the features of quality assessment in accordance with European standards are as follows. Simplicity, relatively low costs, good reliability, and repeatability. So the main disadvantages, however, are the use of basic conditional quality indicators, such as penetration and softening point, which indirectly characterize the performance of the binder in asphalt concrete, and the limited ability to predict the service life of road surfaces using these parameters. So the EU standard does not provide for the determination of the amount of evaporated dilutant, nor the softening point of the residue after heating. Still, nevertheless, the European system for the standardization of bituminous binders is quite balanced in terms of the cost of experimental work, and it corresponds well to the current stage of development of bitumen technologies. And we can finally go to the next slide. All right, so let's talk about some of the methods of modifying bitumen, maybe some alternative methods. So first of all, let's talk about rubber crumb. Rubber, from the point of view of disposal of used tires, which is a big problem, as you know, all over the world, and all other various rubber products, the use of crumb rubber is of great importance for producing modified bitumen. This is one of the reasons for this modification method, all in all. So it's very feasible environmentally to organize a large-scale disposal of worn-out automobile tires and other waste of industrial rubber goods, and these can all be used to modify bitumen. Some of the other reasons for this are the low cost of the modifier, because cost of rubber crumb is on average 5 to 10 times lower than the cost of rubber and polymer additives such as SBS. The resulting quality of modified bitumen is quite high. It's not at all inferior to the quality of bitumen modified with synthetic rubber polymers. So when making bitumen rubber compositions, we need to follow the technology process very precisely, and it involves complete homogenization of a mixture of bitumen with the crumb rubber, followed by vulcanization, leading to cross-linking of those micromolecules. The traditional technology for making a homogeneous RBB, meaning rubber bitumen binder, provides for mechanical mixing of rubber crumb from 5 to 30% by weight with bitumen. That could be tar, recycled asphalt, or any mixture of the above. The temperature of the process is 150 to 250 centigrade, and the time it takes to mix is about 30 minutes to 24 hours. And it's done in the presence of surfactants or plasticizers. And the swelling process of the crumb rubber and bitumen is shown specifically in this slide. You can see how the rubber particle absorbs the light fraction of bitumen and starts swelling. And in stage 2, you can see a formation of a gel. So as a result, an independent rubber bitumen matrix is formed in this binding material. Numerous studies and experience of RBB application show that modified binders have higher performance properties in comparison with traditional bitumen. The obtained RBB has higher heat and crack resistance than bitumen that is made from the same raw materials, but without the addition of rubber crumb. Next slide, please. So data on the properties of binding material obtained by combining crumb rubber 20% with oil tar, the temperature of 220 to 230 degrees centigrade, and 4 hours of treatment. You can see those in this table in this slide. All right, so the following slide, we're going to talk about the advantages of asphalts obtained from bitumen modified with crumb rubber. And these are reduced noise pollution from the roads, and the reduction is significant. So the noise is reduced by 50 to 70%. And this makes it possible to actually build roads much closer to residential areas without affecting the environment by noise. The service life of such roads is increased by 5 to 10 years, and this is achieved because cracks form much less often on the surface, and this obviously saves money on road repairs. The road surface becomes more resistant to deformation. Bitumen modified with crumb rubber adds elasticity to the road surface, and as a result, rutting is reduced by as much as 75%. Traction of vehicle wheels with asphalt is actually improved. On such roads, statistically, the number of serious vehicle accidents, is reduced by about 50% because the wheels are less likely to skid. The grip properties are also very good in wet weather. The road surface retains its operational properties at high temperature. So when the temperature rises, the traditional asphalt concrete pavement starts to melt at about 47 C. And a layer with addition of polymers retains its shape at ambient temperature up to plus 70 C. And at low temperatures, rubberized asphalts cracks much less. And so these roads with this material can be built in just about any climate zone. Also, with the addition of crumb rubber, the mass of asphalt decreases because part of the volume, actually up to 10%, is taken up by rubber, and rubber is lighter per certain weight than bitumen, so we save on that. The reflective properties of such a road surface are reduced, meaning light reflecting surfaces, and that improves driving comfort and also safety. This material improves the drainage properties of the pavement and prevents damage to the road surface during heavy rains. And the service life of automobile tires is also increased because of the slower wear of the tread. Now we're going to look at a different method of modification. So can we go to the next slide, please? Right. So the next method we'll look at is modification of bitumen with sulfur. Sulfur solution, so to speak. The addition of sulfur increases strength, heat resistance, crack resistance, adhesion, and chemical resistances of road bitumen. The temperature of sulfur introduction, its content, and mixing time have a significant effect on the properties of modified bitumen that we receive. So when developing a technology for the use of sulfur in road construction, it's very important to minimize the release of hydrogen sulfide and sulfur oxides during the preparation and use of sulfur bitumen binders. And we also need to consider the corrosion of the production equipment because, sulfur is that way. So it was found that when sulfur is heated to 180 to 220 degrees centigrade, harmful gases are in fact emitted. While if the temperature is reduced to a range of 120 to 145 degrees centigrade, and if the sulfur content in the mixture does not exceed 20%, then there is no much danger of such release that would exceed the sanitary norms and health standards. There is also the increased corrosion of equipment compared to the conventional technologies. That's something to be mindful of. So with the addition of elemental sulfur, its content in asphaltenes noticeably increases, and the influence of all of the three factors is noticeable. Those factors being the amount of added sulfur, the duration of the mechanical or physical activation, stirring basically, and the heat treatment. Moreover, the stirring and the heat treatment are to a degree interchangeable. The sulfur content in the binder can reach up to 60 or 70% of its mass. The optimal conditions for modifying bitumen with sulfur are as follows: a process temperature of 120 to 140 degrees C, mixing temperature approximately 10 to 20 minutes, depending on the actual amount of sulfur that is being introduced. And the amount of sulfur that we introduce into this bitumen should be about 5 to 7% of the mass. So the modification significantly improves such indicators and as extensibility by actually 22% at 25C and 40% at 0 centigrade. It improves elasticity by 20% and also improves adhesion. So it's essential that the introduction of sulfur up to 7% of the mass reduces the brittleness temperature of bitumen by as much as 2 degrees, which affects the durability of the road surface. And with a decrease in the brittleness of bitumen by 2 degrees centigrade, the time of intense cracking is lengthened by, say, 2.5 years or so. In addition, a decrease in viscosity is observed, 20 versus 24 millimeters per second in the original bitumen. And with a further increase in the sulfur content, the viscosity again begins to increase. So the effect of reducing the viscosity is very significant because it allows to reduce the power costs and the consumption of energy in the preparation of asphalt concrete by reducing the heating temperature of bitumen required for the process. So with the introduction of more than 7% of sulfur, the quality indicators of bitumen are somewhat reduced, but they still remain at a higher level compared to those of the regular bitumen. Apparently, with the introduction of more than 7% sulfur, part of it dissolves on bitumen, plasticizing it, and part of the sulfur remains in the solid state, the crystalline state, providing a certain structuring effect. However, there are also negative aspects of this modification method. First, a ready-made road bitumen is shipped to the consumer at temperatures of 160 degrees centigrade. Modification of bitumen with sulfur at this temperature leads to the formation of hydrogen sulfide and sulfur oxides, which are toxic. In view of this, pre-cooling of the finished bitumen to 120 degrees C is required before modification, and that creates certain inconveniences. Next slide, please. All right, so let's talk about adhesion for a second. The quality of road surfaces and their durability largely depend on the adhesion strength of bituminous binders with mineral materials. A consequence of the lack of strong adhesion to bitumen to the surface of mineral materials is insufficient water and frost resistance. These cause erosion, peeling, chipping, cracking, and all sorts of things we do not want. Adhesion is the interfacial interaction between contact and surfaces of different nature. And adhesion provides a connection of a certain strength between two different bodies. Silicates that are used in road construction generally adhere poorly to bitumen, especially in the presence of water. And this is because the surface of sand and gravel particles usually has a pronounced hydrophilicity, and as a result, bitumen is absorbed only due to the micropores and defects on the surfaces. Water penetrating through the pores in the asphalt concrete to the bitumen mineral material interface gradually displaces that bitumen film and destroys the road surface. So chemical modification of bitumen with adhesive additives allows to a large extent to solve this problem of adhesion to mineral material. Surfactant molecules concentrate at the bitumen stone material interface, and they act as a bridge or glue between the bitumen and the stone material surface, resisting the displacing action of that water. There are a number of surfactants that can be used in road construction that can be anionic, cationic, or non-ionic. The most effective adhesive additives are cationic surfactants based on nitrogen-containing chemicals such as imidazolines, amidoamines, and amines. By reducing the tension at the bitumen mineral interface, such additives contribute to better enveloping of the grains of stone material with a binder, and they thereby increasing the strength and water resistance of asphalt concrete, and as a result, lengthening the service life of the road surface. So with the use of surfactants, the season of road construction works can be extended because it's now possible to work during precipitation and at lower temperatures. In practice, some of the surfactants used are Bitumen from America, F4 from Germany, Dynaram and Polaram from France, EC06 from Holland, etc. Quite a few additives out there in the market. And these additives are introduced into bitumen generally in the amount of 0.05 to 0.5% or so. Next slide, please. Right. So here are the methods for production of polymer modified bitumen, finally. And as a rule, these methods provide for, or rather require, an increased process temperature, something in the range of 150 to 200 degrees centigrade. and they also involved intensive mixing of components. So PMB is produced in one of the following ways. We can introduce a solid polymer into the bitumen melt. We can introduce the polymer in the form of latex in the bitumen melt. We can bring the polymer in the form of latex into a bitumen emulsion. We can mix a polymer solution into the bitumen melt, or we can introduce a curing agent to the bitumen in addition to the polymer. And it's the combination of bitumen and polymers that contain functional groups. One of the most common is the first method. The polymer is introduced into bitumen in the form of a powder, which in some cases, to prevent sintering, is applied to a mineral filler. Stirring or agitation, as a rule, is performed under strong mechanical strength and at higher temperatures, such as 160 to 180 C, sometimes above 200 C, actually, and the process takes quite a bit of time. The decomposition temperature of most polymers used for modifying bitumen, such as polyethylene, polypropylene, ethylene, propylene rubbers, etc., actually exceeds the temperature of their combination with bitumen by quite a bit. So the reactions of thermal and mechanical destruction of polymers in the bitumen does not occur. And if it does occur, the extent of such reactions are quite insignificant. So bitumen softens when heated, right? So thermoplastic polymers, regardless of whether they were crystalline or amorphous, actually become viscous. The increased temperature accelerates the swelling or dissolution of the polymer in the bitumen. In the production of modified bitumen, two processes are used. There are continuous processes and batch processes for production. In continuous production, hot bitumen and polymer, which can be in the form of a powder or crumb, both ingredients are fed into a coarse premixer, I guess, with precise control of the rate of flow. And at this stage, the bitumen gets in contact with polymers. It's wetted by polymers, so to speak. And after this pre-mixing stage, the bitumen polymer mixture passes through a mill with a high degree of grinding to achieve the desired mixing quality. And then this mixture is sent to special tanks equipped with a mixing system to prevent phase separation, where the so-called maturation takes place. This process depends on the type of bitumen, the type of polymers, the settings of the mill, how the mill works, the flow rate, and then the temperature of bitumen. So in the production of modified bitumen in batches, one or more mixers are usually used, like two mixers, for which bitumen and polymers are loaded in certain quantities. And then they are pre-mixed and sent to the fine grinding mill, through which they pass the required number of times. So it usually runs in a few cycles. A laboratory test is required to determine the actual number of passes through the mill that is needed. And when the mix has been run through the mill for the required number of times, the mixture is ready for use, and it can then be unloaded to an asphalt plant, to a storage tank, or into a sprayer. Next slide, please. Right. So now we come to the practical part, I guess, and we're going to take a look at a globe core solution. It's a continuous bitumen modification plant called USB 3. At this time, the model range is represented by two plants, two models. The capacity of each model is 6 cubic meter per hour and 12 cubic meter per hour, with the possibility of introducing a polymer in the range from 1 to 6% by mass, a plasticizer up to 10%, and an adhesive additive up to 1%, depending on the product formula. However, there are already promising developments underway to expand the model range with capacities of 20 and 40 cubic meters per hour continuously. So the design of our plants allows the use of any modifiers known today, including crumb rubber, various special additives, along with just about all known SBS polymers, which can come in the form of granules, powder, or liquid. The plant allows for new formulations of modified bitumen in which the introduction of adhesive additives and plasticizer is required. So let's take a closer look at the design of this machine. Next slide, please. Right, so on the principle of operation of the USB 3 machine. The system is mounted inside a frame. The dimensions of the frame allow easy transport in a standard 20-foot container. The frame itself is pretty strong physically, so the plant can be quickly deployed or dismantled in the field whenever the location of the asphalt plant must be changed. The bitumen modification process begins with loading the polymer into a hopper. This is done by the operator manually, or it can be done with a hoist or telfer. And after that, the operator sets the percentage of additives in the bitumen on the control panel and starts the plant. And the plant then just runs automatically. So bitumen is heated to 160 to 190 degrees. It's fed into an intermediate tank along with the polymer. The polymer is supplied by an auger or a screw conveyor. If the formula requires a plasticizer or an adhesive additive, then these are dosed into the bitumen before it's fed into the intermediate tank. So a high-speed turbine mixer runs in the tank. It pre-mixes polymer and bitumen, and the resulting mixture is directed to a colloidal mill. And the mill has special profile cutters which grind, cut, and homogenize the polymer containing bitumen. And then the finished product from the outlet of the plant is unloaded into a storage or transportation container. So only one pass through the mill is sufficient for the production of modified bitumen. At the same time, the quality of the binder produced in our continuous plants is not at all inferior to the quality of the binders produced in big batch plants. Moreover, the USB plant is more reliable in operation, we think, due to a smaller number of mixers involved and a smaller number of mills. It's also, we think it's easier to maintain because of the automation of the modification process. And so the cost of the modified bitumen is actually decreased. Operating this plant allows you to set up the production of high quality modified bitumen for large volumes of asphalt concrete mix. Roads that are built with such mixtures last 2 to 3 times longer than the roads that are built with ordinary bitumen. And we can go to the next slide. All right, so let's take a closer look at the design of the plant. As I've mentioned, the following components, all of the basically components of the machine are installed within a metal frame. There are 2 bitumen pumps, M1, M2. There is the mill, M3, the mixer, M4, polymer hopper with an auger conveyor, M5, a plasticizer input unit, M6, adhesive additive unit, M7, and a system of heated bitumen pipelines with control valves also labeled on this diagram, the VT1, VT2, VT3, V1, and V2. Next slide, please. All right, so on this next slide, we have a good look at the process diagram of the plant. So the pump, the M1 pump, takes bitumen preheated to the operating temperature, and it's 180 degrees centigrade. So the bitumen comes from external boiler outside of this plant, and it goes into the system. The amount and the rate of bitumen input can be controlled using a frequency converter. And depending on the position of the VT1 three-way valve, the bitumen can be fed either back to the bitumen boiler or to the mixer. And before the M2 pump, the bitumen is mixed with the polymer using the M4 turbine mixer. The operator takes polymer bags and puts that polymer into the polymer hopper. And from that hopper bin, it's fed by an auger elevator or conveyor into the system, into the process. And the conveyor is driven by the M5 motor. Depending on the required concentration of polymer in bitumen, the operator can actually control the speed of the drive of the conveyor and provide the required supply of polymer. There is a knob on the cabinet, on the control cabinet for that. The M6 pump supplies the required amount of plasticizer to the bitumen before the mixer, and the operator can control the rotation speed of the M6 pump drive and thus provide the required supply of the plasticizer as well. The M7 pump now supplies the required amount of adhesive additive to the bitumen before the mixer, and the operator also can control that speed of the pump and regulate and adjust the supply rate of the adhesive very precisely. In the mixing tank, the polymer, plasticizer, and adhesive additives are distributed in the bitumen evenly. In this tank during the operation, bitumen level is constantly monitored and maintained between the level sensors. There are high level sensor and low level sensor. HLS1 and LLS1 respectively. It's done by controlling the M2 pump using a frequency converter. And this frequency converter operates depending on the signals received from these two sensors. The M2 pump pumps out the polymer bitumen mixture from the M4 mixer. Polymer is that is evenly distributed in the bitumen is ground and homogenized by the mill, M3. So from the M3 mill through the VT3 three-way valve, a bitumen goes the modified bitumen line and goes into a collection tank. And through the VT2 valve, the modified bitumen can be fed by the M2 pump to repeat the mixing cycle in the mill if necessary, after which the bitumen passes through the VT3 three-way valve again. And also through the VT2 valve, this modified bitumen can be returned to the boiler after passing the mill, and this is done by the M2 pump. And after which this mill can go through the entire mixing cycle again with the addition of the necessary additives. Next slide, please. This is a bigger picture, really. This diagram shows the whole facility with the a USB 3 machine shown inside a dashed frame. And this slide shows the whole bitumen facility here. So bitumen comes heated from a bitumen boiler at 190 degrees centigrade. It's stirred by circulation in that boiler first using a separate pump. It's designated here as M1.1. So after the bitumen in that boiler reaches a uniform temperature, this bitumen is then fed to the modification plant through a heated feed pipeline. The plant itself is heated to the operating temperature of 90 degrees by the circulation of heat oil that is provided by the pump M1.3. The hopper is filled with polymer, and then automatic operating mode of the plant is selected. So after pressing the start button in automatic mode, the plant just operates according to the specified sequence. It's all automated. The components farthest from the bitumen input are engaged first. That's the principle. But after pressing the stop button when operating in automatic mode, the plant turns off in the reverse order. And at the end of the work, the unit must be flushed with straight bitumen for easy subsequent startup. Next slide, please. Here we can see the overall dimensions and the connection dimensions of the plant. This can help prepare for placing the plant and to prepare supply and output lines. Okay, and we can go to the next slide. Right, so the plant has a few operating modes. These are modification mode, and then modification plus additives. I'm curious to see if this animation will show us all of the different ones that I'm going to speak about. But anyhow, there is the modification mode, the modification plus additives mode. There is the flushing mode, the finishing mode, the circulation mode, and last but not least, there is the manual mode for manual control of the plant. So let's talk about modification and modification plus additive mode. These are the two main operating modes of the bitumen production plant, bitumen production plant. One of the modes is selected using the mode button, and if you press the start button, then the message activated appears in the top line of the screen, and the process of modified bitumen production starts right away, immediately. So pneumatic valve VT1 switches from bitumen supply to the return line to supply to the mixer, and the bitumen supply pump M1 starts, and the mixer tank is filled with straight bitumen. So when the bitumen reaches the lower level sensor, LLS1, the M4 impeller agitator is switched on, the screw conveyor motor M5 and the M3 mill driver also started. So when the mill spools up to its full RPM, the M2 feed pump starts, and after passing through the mill and the VT3 valve, the polymer modified bitumen enters the maturation tank for storing of the finished product. Next slide, please. This here is the modification plus additives mode, and if this mode is selected, the drives for the supply of plasticizer M6 and the adhesive additive M7 are also started, and Through the viewing port, there is a side glass. You can observe the frequency of the conveyor for the plasticizer. And if necessary, you can adjust the amount of the supplied polymer, plasticizer, and adhesive additive by just changing the frequency of on the converters. So when the high-level sensor HLS1 in the mixer is reached, the M2 pump converter increases the frequency to 60 Hertz. If the bitumen level in the mixer decreases, then after 30 seconds, the converter of the M2 will decrease its frequency to 50 Hertz. So when the level increases to a high-level sensor, the frequency rises again. So the bitumen level in the mixer is maintained continuously between the HLS1 and LLS1 sensors. If the stop button is pressed during operation, the unit enters the flushing mode. So there's the finishing mode. A blinking finish message appears in the controller screen. And what happens is the M1 pump stops, the VT1 valve switches to supply bitumen to the return line. M5 screw conveyor turns off. The M3 mill, M4 mixer, and M2 pump, however, continue to run. When the LLS1 sensor no longer detects bitumen, the M4 mixer stops. And after a certain time period, when the mill current drops below a specific setting, the M2 pump and the M3 will also stop the mill. And at that point, the active and finish messages disappear from the screen, and this means that the process is now complete. And the condition for the successful startup of the plant is that the temperature of the thermal oil in the unit is not lower than 160 degrees. That's important. Because if it's below, then there is a warning message, and the operator will not will not be able to start the plant. Also, if the low-level sensor in the mixer is active, if it's detecting bitumen, the plant cannot be started. Next slide, please. Right. So this here is the finishing mode. This mode is used if the plant was stopped for some reason during the process, and if it's necessary to remove and pump out the bitumen that is in the mixer now. So after selecting the finishing mode using the mode button, the operator just presses the start button. We have the activated message on the controller screen. If the low-level sensor, the LLS1 that I mentioned, is on, then the M4 mixer and the mill M3 are switched on. And after the mill spool up, again, the M2 pump starts. Bitumen is taken from the mixer in the same way as in the modification mode process. And after M2 and M3 stop, the active message disappears from the screen and the finish process is complete. So PMB in this mode is output into the product storage container. Next slide, please. All right. So this mode, this is the, one second. Can we go back to the previous slide, please? Yeah, thank you. The flushing mode now. This mode is used if it's necessary to flush the plant with straight bitumen, to preheat the plant before starting or after completing work on the unit before shutting down. In this mode, it's possible to start the plant with a temperature of 140 degrees centigrade only. So after selecting the flushing mode using the mode button, again, the start button is pressed, the activated message on the controller screen. What happens is the M1 pump turns on and the VT1 valve switches to supply bitumen to the mixer. When bitumen reaches the lower level sensor higher level sensor HLS1, the mixer M4 is switched on. The pneumatic valve VT3 switches to the position to supply bitumen to the return line. The mill M3 is switched on. After flushing, that bitumen goes to the storage tank. And after the mill spools up, the M2 pump for PMB starts as well. All of these components run for about 60 seconds, maintaining the bitumen level in the mixer. And then the bitumen supply pump M1 stops. The VT1 valve switches to supply bitumen to the return line. And the bitumen is worked from the mixer. And when the low-level sensor 1 is off, the VT3 valve switches to supply bitumen to the outlet. The M4 mixer stops, and the bitumen from the mixer starts flushing the pipe and the finished product storage container as well. So after a while, when the mill current falls below its setting, the M2 pump and the mill M3 stops. And after stopping the mill, the VT1 valve switches back to the position of feeding bitumen to the mixer, and the M1 pump is turned on in reverse. So the remaining bitumen is pumped out of the pipes for about 20 seconds. And this is now when you can turn off the plant, or if you need to, you can select a different operation mode. And I guess the final mode we'll talk about in some detail is the circulation mode. Next slide, please. Thank you. So this mode is used if it's necessary to run the polymer modified bitumen from the finished product container once again through the mill, circulated. So we select circulation mode using the mode button. As usual, press the start button. What happens is the VT2 valve switches to the repeat cycle position. The VT3 pneumatic valve switches to supply bitumen to the return line, and the bitumen supply pump M2 starts. And at this point, the PMB is pumped into the buffer tank. And after pumping out the PMB, we can start the modification or modification plus additives mode as necessary. Next slide, please. And in terms of manual control, this manual mode is used when it's necessary to test operation of individual components of a plant. It's used during startup and commissioning and for adjustments to the process, and if necessary to return the plant to its initial condition if a failure or an emergency stop occurs and we need to reset everything back to what it was. Next slide, please. All right. Okay, one back, please. One slide back. Next one, thank you. Next one. Thank you. So let's talk about the mill. The heart of the plant is the mill. It's the colloid mill. The pumping equipment of the plant has frequency converters. So all of these pumps allow premixed bitumen and polymer to be supplied to the mill at a given rate at a certain pressure. So that relieves the mill from the suction and discharge function. So all of that power can be applied only to the process of homogenizing the product. The cutters of the mill have a special profile, and that profile allows all sorts of things to happen. There's grinding, cutting, homogenizing, polymer containing bitumen. So basically, we obtained a finished product of excellent quality in just one pass. The design of the mill also allows, obviously, to change the gap between the cutters. That may depend on the product, the formula, and a few other factors. Next slide, please. So now let's talk briefly about the advantages of the USB 3 machine. Some of the advantages are the ability to use any modifiers known today, including crumb rubber and various special additives and every known SBS out there, which can be supplied as granules, powders, or liquid. It is capable to produce any number of products with different concentrations of additives, so there's a lot of flexibility in that. It's the excellent quality of the product with little time required for the process. It's a rather fast machine. It's easy to operate and maintain. It's quite small in size, so that means it's easy to transport from place to place in a standard 20-foot container if necessary. The structure that it's built in, the frame, allows for quick assembly and disassembly of the machine in the field, and that's very important when changing the location of the plant. The intermediate tank is designed for preliminary mixing of the polymer with bitumen, and it increases the bitumen polymer contact time, which takes some of the load off the mill. The tank itself is equipped with a high-speed agitator, which allows mixing the bitumen and polymer evenly. The level sensors are installed in the tank to maintain a constant level of bitumen for optimal mixing conditions. The plant is equipped with electropneumatic valves. Compressed air for those can be supplied from the compressor that comes with the plant. It's optional, but recommended. And that allows the plant to be independent from any external compressed air sources. All of the bitumen pipelines, pumps, the mill, the intermediate tank, they all have oil heating. Heating with such heating with thermal oil is the most gentle and efficient heating process for components and for the bitumen pipelines. And the control system has a control cabinet that contains switching equipment, motor protection circuits, frequency converters, the soft starters for the mill drives and the pumps. There is a controller, a PLC controller, and all of the measuring transducers that are made by big companies such as Emerson, Siemens, ABB, Autonix, etc. So very good quality components in that. The controls of the plant are on the front panel, and basically there are a few buttons: start, stop, mode, alarm, reset, emergency stop, and there are buttons for manual control of components. There is the controller panel, and there are pressure and temperature controllers and readouts. An important feature of this plant is the complete automation of all processes for the production of PMB. For ease of controls, the screen, basically the cabinet is equipped with a mnemonic diagram of the plant with signal lights. And it's basically just a simplified display of the process diagram, but it allows the operator to quickly identify components and manipulate them as necessary. The plant uses a software algorithm embedded in a PLC, and using that software, the operator can quickly customize the process settings. The PLC can be reconfigured via the internet remotely, and it's pretty good at detecting errors. The PLC is quite reliable, and it does speed up the setup and commissioning of equipment and startups quite significantly. Some of the other things that can be used with the plant optionally is a sulfur supply section, polyphosphoric acid supply section, and a lifting device with scales to use the big bags for the polymer if necessary. A compressor comes with the plant optionally, and the mill that is installed in the plant can be equipped with the mechanical seals. That is also customer choice. And next slide, please. Right, so, okay, we were talking about a big machine, but Globcore also offers a smaller unit, which we call the laboratory unit for bitumen modification. And that allows one to experimentally determine the optimal formulation for the product. Or maybe it's necessary to change the formulation at the main product site, but it's easier to run an experiment on the smaller mill. It's designed for preparation of modified bitumen in rather small volumes, so 12 to 20 liters per cycle. This unit is much smaller than any full-scale industrial plant, and it consumes significantly less power, obviously. The transport dimensions are just a bit over a meter long, a bit under a meter wide, and 1.5 meters high. And the power consumption for this plant is below 5 kilowatt. So for the preparation of modified bitumen, we use here the inline mixing with the simultaneous dispersion of bitumen and polymer using a mill. The design of the unit also provides for adding liquid components into the modified bitumen. Now, I'll talk about that in a second. So on this slide, you can see the components as they are installed on a welded frame labeled 1. The loading of bitumen and modifying additives into the reactor, position 3, is performed through a loading hatch, position 4. If necessary, the liquid components can also be added via the same hatch. Excuse me. Maintaining the operating temperature range of heated bitumen is ensured by heating the tank and all the pipelines with sections of heating cables and cord. Keeping the temperature of bitumen in the operating temperature range, and that is 160 to 180 centigrade, occurs with constant stirring using that mechanism labeled 5, and it's controlled automatically. The temperatures of bitumen and the surfaces of the components are monitored using temperature sensors, and they're displayed in the control cabinet in position 8. The components are driven by electric motors through elastic couplings. And the uniformity of the process of dispersion of the polymer and bitumen is ensured by constant mixing of bitumen during its circulation through the mill in position 2. A circulating flow of bitumen is created in the pipeline system 7, and the finished product is pumped out by the bitumen pump in position 6. So looking at the flow diagram, let's look at the operation of the machine real quick. First, the operator checks the position of the valve V and the bottom valve BV. They all must be completely closed. Then the operator starts the heating process. The control system can hold temperatures within specified limits, for example, 160 to 180 degrees. And when the temperature in the mixing tank reaches above 160 degrees Celsius, we load the reactor R with hot bitumen at 180 degrees. And this is accompanied by a green signal light on the control panel. And that means that the mixer can now be started. After that, the operator presses the green mixer button on the control cabinet and the mixer starts. And then we can add pre-weighed portions of polymer modifier, adhesive additive, and plasticizer to the reactor. Excuse me. The introduction of the additives requires the bitumen to be at a certain operating temperature, and that temperature is selected according to the polymer specification. So then, after a certain amount of time has elapsed for pre-mixing the components and the bitumen, the operator then can open the bottom valve the valve itself has a rotating handle under the mixing vessel, and the operator turns on the mill by pressing the green mill button on the control cabinet. So if the mill temperature, however, is not within the required limits, the mill will not start. The temperature must be just right, and the mill starts, and then the bitumen mixture will begin to circulate, returning to the same container after the mill. And if the mill does not turn on and the green light next to the mill label is off, that means that the pipeline with the mill is has not yet reached the necessary temperature for the process. So for about 1 hour, that bitumen stays and matures in the reactor with the stirrer and the mill on. And after that, the operator places a container under the drain outlet and opens the valve V and turns on the bitumen pump. The modified bitumen will then flow from that outlet. However, it's recommended to first drain the first few seconds, I guess, 2-3 seconds, drain into some bucket for disposal. And then you can use an actual sampling container, take an actual sample for laboratory analysis, if you understand what I mean. So after draining that prepared bitumen from the tank, the residual bitumen should also be drained from the mill, from the outlet, from the pipelines, etc. So to do this, the operator must close that bottom valve without turning off the bitumen pump. And in this case, all of that remaining bitumen is pumped from the mill and the pipelines. And after complete draining of bitumen from the system, the operator can then turn off the pump by pressing the red bitumen pump button and close the valve B. So as you can imagine, the laboratory unit would be especially relevant if the facility plans, for example, to sell the product to outside customers, and it then becomes very important to keep the product quality high when you switch from one recipe, one formula of the product to another. You need to get it just right. So with this, we conclude our presentation. We can go to the next slide, please. Thank you. That's what I wanted to show you. And I hope it's been at least somewhat interesting and educational for you. I'd like to thank you very much for being here today. This lecture, I guess, has been a bit on the longer side, but I hope everything was fine. And I believe my colleagues answered all of the questions that you asked in the chat. Right. So once again, it was a pleasure of presenting this information to you today, and I do hope to see you all in the future. Oh, one thing before I forget, if you need to receive a certificate of participating in Globe Cortex School, please write us. We'll get you those certificates, email them to you, and okay, we can do that. And with this, stay tuned, visit our website. We constantly have new programs and new webinars on different topics and old topics and new topics. So I hope to see you all there, and I will speak to you then. Thank you and goodbye.